Hey everyone, what we're going to do here is I'm going to go through the motion sensor lab, this worksheet here. We either did it in class, so you can use this as review, or if you weren't here, you can use it to follow along with what we did in class. We're using a motion sensor, which looks like this. The motion sensor sends out sound waves that bounce off objects and returns to give you an accurate description of how far away something is. It's plugged into the computer here, so once I start with the play button down there where it says record, it will map out the position of the object. So we'll go through each scenario 1 through 11. So what we're seeing here is that the position graph is a flat line for number 1, meaning that I stayed around this 0.5 meter mark the entire trip. If I look at the velocity graph here, you can see the green data is 0 the entire time. So the object was not moving during the entire trip. Okay, scenario 2 here shows the position increasing as time goes on as I walked away from the sensor. So I have a nice positive slope. My velocity graph was around 0.3 meters per second the entire trip and nice and constant. So it was not on 0 this time, it was above 0 as a flat line. Okay, here's scenario 3. Starting around 2 meters, you can see I'm walking back towards the sensor, and the slope is now negative, but it's not as steep as the last graph. When I go to the velocity graph, I can now see that my velocity was around negative 0.2 or 0.3, and I was nice and steady the entire trip. So my velocity is now below the 0 line, just meaning I went backwards. Here's scenario 4. Started close to the origin, walked away from the origin, and then my position remained the same. So if I flip over to velocity graph, you can see my velocity was positive for the first few seconds, and then it dropped down to 0 once we got to that portion where I stopped moving. So velocity was positive, then velocity was 0. You'll notice I can't do extremely quick breaks in my velocity like the worksheet has you do. But that's because I'm a human being and I can't stop instantaneously. I do have to slow down when I try to stop. Scenario 5 is actually the reverse of this. If you are downloading the worksheet, I flip the graph, and so instead of a positive slope, it's going to be a negative slope to a flat line. Here's scenario 5. Walking back towards the sensor this time, but then stopping at around the 7.5 second mark. Here's my velocity graph for that again. I have negative velocity for the first few seconds, and then it goes to 0 when I reach around that 7.5 mark again. So negative velocity turns into no velocity when we reach that flat line. Scenario 6. Scenario 6, you can see me moving away from the sensor, and around the 2.5 second mark, I start moving faster away from the sensor. So here's the velocity graph for that one. You can see me moving in the positive direction with a positive velocity, and around the 2.5 second mark, I go up to a higher positive velocity. This should be a nice flat line again. I'm just a human, so I'm not perfect. Alright, scenario 7 here. You can see a walk away from the sensor, then a stop, then a walk back towards the sensor, and the difference here is this slope is much steeper, so I should see that in my velocity graph. Okay, again, not perfect because I am a human. Here's my positive velocity for the beginning. It drops to 0 for a few seconds, and then you can see me going with negative velocity. Much faster because I'm much further away from that 0 line. Okay, here's scenario 8. In scenario 8, you can see a nice negative slope here with a flat line to 0, and then a slight gradual positive slope. So I was walking backwards quickly, then I stopped, and I was moving away from the sensor at a nice slow rate. Okay, and here is the velocities for that. You can see very negative velocity in the beginning, meaning coming towards the sensor, 0 for a few seconds, and then a very small positive velocity as I walked away. Scenarios 9 through 11 here give you the velocity graph and would like you to recreate the position graph. So if you didn't do this lab, I'd like you to try that on your own and show me what you got. I'll do a couple motion maps for you to show you what you should draw when you see your motion maps. So I'm going to do a couple motion maps here for you for the lab we just did. I'm not going to do every single one. I'll do a few, and I'd like you to see your work on this as well. So for scenario 1, the object was not at the origin. That would be inside the sensor. So the object was, say, it was 2 meters away and did not move, so the object stayed in the same position as time went on. In scenario 2, we started not at the origin again, but we were moving away from the origin. We started near the origin, and you can see I covered the same ground each second. And to show how I go from one direction to the next, you can see these are my velocity arrows. Each velocity is about the same length, and to make sure that makes sense, we draw the tick marks to show that they're all the same length. So every dot represents where the object was in its position, and the arrows represent how fast you're going. Okay, in scenario 3, we started away from the origin, but this time we went slower. So being slower, the dots are much closer to each other, and to connect us from one motion to the next, you draw your arrow from one dot to the next. However, this time the velocities are much smaller. You can see the arrows are much smaller, and I can indicate their different speeds by putting different dash marks there. So the dashes represent a different speed. 2 doesn't necessarily have to mean faster, it just means that it's different. And the last scenario I'm going to do here is scenario 4. Scenario 4 was the object moving away from the origin at a nice steady pace, and then reached a certain point and stopped. To connect one dot to the next, again, draw your velocity arrows, and when we reach that point that we stop, we know that we don't have to have an arrow anymore because we're at the same location every single second. So for the rest of the problems, make sure you have a written description, a motion map, and you have a velocity and position graph to know where an object is and how you can represent that it's moving